Today's session is about number system in the topics related to mathematics, grade 9 CBSE syllabus. So let's see what number system deals with. Many a times in mathematics we have dealt with different types of numbers, the number line. So these types of numbers which are dealt, like the decimals, like the fractions, or the numbers in the power form, have got different types of classifications in mathematics, which we are going to discuss in brief in today's session of number system. So let's see the different types of numbers classified in the branch of mathematics. Coming with natural numbers. What are natural numbers? Natural numbers are the numbers which cannot be expressed in fraction form other than the denominator being 1. Say for example, I take the natural numbers to be starting from 1, 2, 3, 4, 5, so on and so forth. The reason being that it cannot be expressed in a fraction form but can be expressed on the whole with denominator as 1. Say for example, I can write this as 1 by 1 and this as 2 by 1, this as 3 by 1, and etc. So natural numbers cannot be expressed in fraction form other than with denominator being 1. And the numbers which are positive and start with 1. So 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth till infinity are called natural numbers. And usually the natural numbers are denoted by capital N. Capital N equals 1, 2, 3, 4, 5, 6 is the set of natural numbers. We write this as set of natural numbers denoted by capital letter N is what we call natural numbers in mathematics. Let's see how we can deal with different examples and understand natural numbers more better. Let's try with different types of examples. For example, I would like to test if the number 5.9 is a natural number. So my question is 5.9 a natural number? Now let's see the answer for this question using the basic definition as we have learnt in the previous session of natural numbers. Now 5.9, if I take this right down here, I understand that it is a decimal number to the approximation of one decimal place, and this in turn can be written in the non-decimal form as 59/10. So 5.9 indirectly can be written as 59/10, which breaks the rule of a natural number because the natural numbers accept only the denominator as 1. Other than 1, any other number we take cannot be accepted in natural number. Therefore, this not being equal to 1 is not a natural number, strictly by the definition as we have learnt. So 5.9 is not a natural number. And I write this as 5.9 does not belong to the set of natural numbers, is how we understand identifying a natural number or not a natural number. Let's see many other examples to understand the concept more better. Now let's see the other types of examples to understand the natural numbers more better. For example, my next question out here is root 9 a natural number? Now the question here is, all the numericals which are expressed in the form of roots cannot be a natural number because it is not directly in the numerical form, is point number 1, which I identify in the stage 1 of this being a natural number. Secondly, let's see if I can further simplify this to get a more simplified answer. We clearly know that 9 is a perfect square so that root 9 we all know is equal to 3. Root 4 is 2. Root 16 is 4. Root 25 is 5. And hence root 9 is 3. Now, because this can be indirectly expressed in the form 3, we understand that root 9 is equal to 3, and clearly 3 is a natural number. And therefore, indirectly root 9, which can be expressed as equal to 3 after its simplified form, is a natural number, belongs to n, is how I understand the unsimplified questions given to be identified to be a natural number or not a natural number. So what do we understand from this basic example is that whenever a question is given about testing on a natural number or not a natural number, we try to simplify it to the most simplified form. It is very important to note that until and unless a given problem is simplified to the most simplified form, we cannot judge on the number being a natural number or not a natural number. Let's do one more example. Is 5 cubed a natural number? This is my question. Yes, let's see. Or let me add this to it. Now, is 5 cubed by 25 a natural number? So the first thing what I do is I try to reduce this to the most simplified form, and then I get to identify on the final justification of whether this number is a natural number or not a natural number. So let me take the given problem 5 cubed by 25, and let me try to simplify this more further and then justify on this natural number concept. Now we know that 5 cubed is 5 times 5 times 5, and 25 can be written as 5 times 5, and then the two 5's get cancelled out here. Then finally I am left with only one number, which is 5. And that clearly makes me understand that the given question 5 cubed by 25 is nothing but indirectly the simplified form of 5. And then this we all know belongs to natural number. Therefore, 5 cubed by 25 is a natural number, is how we justify through the most simplified form and then justification through that. Next, let's go with another example to understand the natural numbers more better. Now the question here is root 49 plus root 4 by root 9 a natural number? So here we see that there is more part of which to be simplified before we justify on this given number being a natural number or not a natural number. So the given question being root 49 plus root 4 by root 9 is to be further simplified, as we clearly know that root 49 is 7 and root 4 is 2 and root 9 is 3. I reduce them into the non-root form by using the perfect square number concept. And using this, I clearly understand that 7 plus 2 can be added further to get 9, and the denominator is 3. So that this can be further simplified, as we know that denominator and the numerator get cancelled for 3 times in the numerator. So 3 1s, 3 3s. My final answer is 3 for the given problem. So the most simplified answer for this is 3, and which is clearly a natural number. Therefore, the given number is a natural number. Therefore, root 49 plus root 4 by root 9 is 3, which is clearly a natural number, belongs to the set of natural numbers, capital N. The next set of numbers in the branch of mathematics is the whole numbers, continued from the set of natural numbers. So what are whole numbers? So let's discuss about whole numbers in this session. Whole numbers are the numbers which start from 0. It's very simple because every natural number along with a 0 is a whole number. Say for example, I have my natural numbers revisited to be 1, 2, 3, 4, 5, 6, etc. up to infinity is what we have discussed in the previous session. Then whole numbers is nothing but natural numbers, and including 0 is what we identify the difference between natural numbers and whole numbers. So with this we understand that the set of whole numbers is 0, 1, 2, 3, 4, 5, with the only additional difference being 0 between the natural numbers and the whole numbers. 0 along with a natural number is a whole number, is how we identify through the words. Zero along with natural numbers is a set of whole numbers, and this is denoted always by capital W. 0 along with natural numbers is a set of whole numbers denoted by capital W. Let's do some example problems to understand the concept of whole numbers more better. Now that we have understood about the whole numbers and the difference of whole numbers as compared to the set of natural numbers, let's try with some example problems to understand the concept more stronger. For example, I have is (7.1) a whole number is my question. 7.1, let's try to see if it can be expressed as a whole number. So I take the number 7.1 out here, and this, when I express it in a non-decimal form, can be expressed in the form 71/10. So 7.1, the decimal form, is expressed in the non-decimal form 71/10, and this clearly states that because the denominator is not 1, and as we have discussed about the natural numbers and the whole numbers being all natural numbers including 0, this cannot be a whole number. It is instead not a natural number too. Therefore, 7.1, which is expressed in the fraction form, cannot be a natural number, and equally this also cannot be a whole number, is how we understand the concept of whole numbers. Now let's try to see some complex examples to understand the concept of whole numbers more stronger. For example, I have the question which says is √32 minus 2 power 5 a whole number. Or I take this to be √64 minus 2 cube a whole number, is the question I have put forth here. So for this, let's try to see the justification of this being a whole number or not a whole number by first trying to simplify the given number, because every number which is being justified demands for the most simplified form. So let's try to simplify further and then justify for this number being a whole number or not a whole number. The given question is √64 minus 2 cube. As we know that √64 is 8, because 8 square is 64 under root, which gives me 8. So √64 is 8 minus 2 cube, which we know is 2 times 2 times and 2 times which further gives me 2 2's 4, 4 2's 8, and this finally simplifies to 8 minus 8, which is 0. Now I have the most simplified form of this to be 0. So 0 is a whole number, as we clearly know that the set of whole numbers start from 0, 1, 2, 3, etc. Therefore, this belongs to whole number, that is indirectly root 64 minus 2 cube is a whole number. Also, it is very important to note that this is not a natural number, but root 64 minus 2 cube is not a natural number, because we have clearly seen that n starts from 1, 2, 3, etc. and whole numbers start from 0, 1, 2, 3, etc. And therefore, this is where I have this belongs to W, but here it does not belong to n. 0 is part of whole numbers, but 0 is not part of natural numbers. Is how we understand the difference between set of whole numbers, capital W, and set of natural numbers, capital N. Integers. The next set of numbers in the field of mathematics after the natural numbers and the whole numbers is integers. And this plays one of the most important role in the set of numbers in the number system. So let's see what are integers or set of integers in the field of mathematics. Integers are denoted by capital Z or capital Z, and it is nothing but the set of all numbers, natural numbers and whole numbers, which are both positive and negative. So in the most simple understanding, I understand that the set of integers is the natural numbers and the whole numbers taken both in the positive side and the negative side. Say for example, let me start with the positive side. We know that the whole numbers are 0, 1, 2, 3, 4, 5, etc. up to infinity is what we understand the natural numbers or the whole numbers added with 0 in the positive side. So integers also include the negative part of it. Say for example, I have all the positive side on the right side, then I have all the negative numbers on the left. Minus 1, minus 2, is how we frame the complete set of integers in this form of the positive side being the natural numbers of the positive sign, and the left side being the negative numbers of the natural numbers which are negative in sign divided by 0. So I have all this to be positive natural numbers and all this to be negative natural numbers along with 0. So positive natural numbers plus 0 plus negative natural numbers together make the set of integers, is how we understand the difference between the natural numbers, the whole numbers and the integers, the set of integers being denoted by capital Z. Also, it is very important to note that the set of integers is again further classified into positive integers and negative integers and non-negative and non-positive integers. So let's see how the classifications are done. Say for example, I have the set of integers. Then I have 4 types of classifications for this. The first being positive integers denoted by Z plus. And next is negative integers denoted by Z minus. And thirdly, I have non-positive integers. And next I have non-negative integers. So this set of integers denoted by z, which has both the positive and negative signs and the neutral 0, is classified into 4 types, which is very essential to understand before we understand the entire set of integers z. So this is classified into positive integers denoted by z plus, negative integers denoted by z minus, and non-positive integers and non-negative integers. So let's see what each of them differs with. Z plus, as clearly mentioned for positive integers, states that we pick only the positive part of the integers. So we know that the positive integers start from 1, 2, 3, 4, 5, etc. Therefore, this set Z plus has all the numbers which start from 1 and end till infinity. So set of positive integers denoted by Z plus is now 1, 2, 3, 4, 5. Similarly, the negative integers Z minus is all the numbers which come on the negative side, that is on the left of 0 of the main set of integers Z. Therefore, negative integers denoted by Z minus starts with minus 1, minus 2, minus 3, so on and so forth. Is how we write the set of negative integers. Similarly, let's see what does this non-positive and non-negative integers differ with their definitions as compared to these. It is very important to note that both look similar, positive and non-positive. So let's see how the difference comes. So positive integers is 1, 2, 3, 4, 5, and non-positive integers is all those integers which are not positive. Now, before we come into classification of non-positive and non-negative integers, let's try to make a very important note that 0 is neither positive nor negative. It is neutral, neither positive nor negative. It is neutral, is how I understand the importance of 0 in the branch of numerals. So 0 is neither positive nor negative. It is neutral. Therefore, when I say non-positive, I include all the non-positive integers which are neither positive but only negative, but even 0 included, because even 0 is a non-positive integer. So it comes out to be 0, minus 1, minus 2, minus 3, and so on and so forth till infinity. Now we have the non-positive integers to be 0, minus 1, minus 2, minus 3, so on and so forth. As compared to the negative integers, we clearly understand that non-positive integers is nothing but the set of negative integers including 0, because 0 is a non-positive integer, neither positive nor negative. And therefore, I have this indirectly written as all the negative integers including 0 is how I understand the non-positive integers. Similarly, let's see what does the non-negative integers define. As we clearly know that non-negative indicates all the positive numbers, so I have all the positive natural numbers which come under the branch of non-negative integers and including 0. Therefore, if I have this set which includes 0, which is neither positive nor negative, and including 1, 2, 3, 4, etc. till infinity, then this set is non-negative integer set. So set of all non-negative integers being this is clearly understood as all the positive integers including 0. Therefore, as we have written for all negative integers including 0, now as we have this non-negative integers, we have this to be z plus union 0. the set of all positive integers including 0, which is neither positive nor a non-negative integer, is the set of non-negative integers which is combination of positive integers and the 0. Therefore, I have 4 classifications for z, which has positive integers denoted by z plus, which has 1, 2, 3, 4, 5 till infinity, and the negative integers denoted by z minus includes minus 1, minus 2, minus 3, so on and so forth. And non-positive integers, which is all the negative integers including 0 denoted by z minus union 0, and similarly the non-negative integers, which includes all the positive integers and the 0, is how we understand the different classifications of the set of integers z. Now let's see some example problems to understand the concept more better. Let's see the relation between n, w and z before we go through different examples to justify the set of integers and its identification in the respective manner. So as we have seen, the set of integers denoted by z is all the negative integers, which is minus 3, minus 2, minus 1, and 0, 1, 2, 3, 4, 5, etc. is how we get the set of integers z. Let me also take into consideration the set of natural numbers and the whole numbers. As discussed in the previous session, the set of natural numbers n is 1, 2, 3, 4, 5 and so on, and the set of whole numbers denoted by capital W is 0, 1, 2, 3, 4, 5 and so on and so forth till infinity. Now let's see what is the relation between z, n and w. As we clearly see, let's start from w and then with n and then with z and make a relation between w, n and z. I clearly see that w is all natural numbers including 0. So I can write this as n union the element 0, singleton 0. And I see the relation between z and w to be all the negative integers, as seen, the first half being the negative integers and the right half being the positive integers divided by the neutral 0. So I can write this as z minus union 0 union z plus is what we get. Now set of integers is the union of set of negative integers union singleton 0 and union the set of positive integers. Now with this, I clearly see that the set of natural numbers is nothing but the set of positive integers, because we clearly see the natural numbers matching with z plus, as z plus is 1, 2, 3, 4, 5 and the set of natural numbers is also 1, 2, 3, 4, 5 etc. So z plus is n and z minus is set of all negative integers. So I see z minus is minus n is how we understand the relation between z minus and n, is how we get the different types of relations between z, n and w. Let's see some example problems to understand the set of integers, set of natural numbers and set of whole numbers combined, and understand the identification of a number in each of its classification, either as a whole number or as a natural number or as an integer. To start with an example, my question here is minus 5 by 2 an integer? So the question here is minus 5 by 2 an integer? So let's try to identify the classification of this given number using the concept of the integer or a natural number or a whole number. Now clearly minus 5 by 2 is in the fraction form, which cannot have the denominator as 1, but other than 1 it is 2. and therefore this can be expressed only as a decimal form but cannot be expressed as a non-decimal form with the denominator 1, and therefore this is clearly not an integer, or it is not a natural number or a whole number. So therefore the outcome is minus 5 by 2 is not an integer, is not a natural number, is not a whole number, because we don't have this in the denominator with 1. Let's try to identify with a different example. So for example, I have, is 2 minus 5 cube a natural number, or a whole number, or an integer? So let's try to identify the answer for this question using the properties what we have learnt. Now coming to this, the given problem is 2 minus 5 cube, and I have to justify for this number being an n, a w, or a z. So for this, we come with the rule that I simplified this to the most simplified form, and therefore this, when simplified to the most simplified form, I get this to be 2 minus 5 cube, which is 5 times 5 times 5, and this comes out to be 2 minus 125, because 5 times 5 is 25 and 25 times 5 is 125. This, on further simplification, gives minus 123. Negative 123 is the final simplified answer for this. Now with this, I clearly understand that this is not a natural number, though it can be expressed with the denominator as 1, and a non-decimal number being expressed with the denominator as 1. But this is an integer, because an integer has the negative natural numbers and the positive natural numbers, including the neutral 0. Therefore, I understand that 2 minus 5 cube, which is indirectly expressed in the form minus 123, is not a natural number, is not a whole number, but is an integer, because it is accepted in the set Z. Is how we understand the different classification of the numbers justified through n, justified through w, and justified through z. Now let's try to see the next set of numbers in the number system, rational numbers. What are rational numbers? Now that we have passed through the phase of integers and the natural numbers and the whole numbers, let's try to enter into the concept of rational numbers. But before we discuss its brief introduction, let me just make it very clear that the set of all NWZ form a different branch in the number system. This forms a special branch in the number system because this accepts fractions and decimals, whereas N, W, and Z do not accept the fractions or the decimal representations. So let's see in brief the definition of a rational number. A rational number is denoted by capital Q, and it is defined in the set form as all the numbers which can be written in the form P by Q such that P and Q are integers, the condition being that the numerator and the denominator must be integers in the fraction form P by Q, and most importantly, the Q should not be equal to 0. The denominator should not be equal to 0 is how we understand the set of rational numbers. So whenever we think of rational numbers, we think of this common formula Q, which stands for the set of rational numbers. Let's see more in brief on how we define a number to be a rational number based on this set notation. Let's try with an example problem. For example, I have 7 over 3, and I wanted to just justify on whether this number is a rational number or not a rational number. So clearly I try to classify initially in the form P by Q, where my P is 7 and my Q is 3. So I pick the P, which is 7, and I pick the Q. So P is equal to 7 and Q is equal to 3 are just justified through these two conditions. Now clearly I see that P and Q must be integers for the number written in the P by Q form to be a rational number. So this acts as the rule 1 and this acts as the rule 2 to identify for a number to be a rational number. Rule 1 clearly states my P is 7 and Q is 3. In this example problem, 7 over 3, and clearly P and Q, which are 7 and 3, are integers, which we have discussed in the previous session. So therefore, P and Q are integers is the first test which this passes out here. Secondly, the rule 2 being Q. So let's see what is Q here. Q is 3, and we know that the number 3 can never be equal to 0, and therefore Q is not equal to 0, and this number also passes the test number 2. So with the passing of the two tests, this and this, I can proudly say that 7 over 3 is a rational number, belongs to Q because it passes through test 1 and test 2. Test 1 and test 2, and therefore 7 over 3 is a rational number. Let's try with one more example problem. Say for example, I have the question is (4 by root 3) a rational number? So in order that I identify for this to be a rational number, I have to pass through the two tests, test 1 and test 2. So coming to the number, let me pick the number which is 4 over root 3 and identify each of P and Q from the given number. So clearly I see my P is 4 and Q is root 3. So here my P is 4 and Q is root 3. Now let's try to go through the test number 1. The test number 1 where I have to see that both are integers. Now as clearly I see P is equal to 4 is an integer because its denominator is 1, but I see that Q is equal to root 3 cannot be a numeral which can be expressed in the denominator with 1. This being a root which cannot be further simplified clearly says that this cannot be an integer. Therefore, here P belongs to Z, but Q does not belong to Z, and therefore it fails with test number 1, indirectly saying that this number cannot be a rational number because this fails through test 1, P and Q being integers. Therefore, does not belong to a rational number. It belongs to Q. Let's take one abnormal example through which we understand the rational numbers. Now my question here is 5 by 0 a rational number? So let's see how we can justify this through the test number 1 and the test number 2. Now clearly I see that the number 5 over 0 in the given question should be classified into P and Q, where I identify the P being the numerator, which is 5, and the Q being the denominator, which is 0, as compared to the given set. Now clearly, going through the test number 1, I see that the P and Q are integers, which is an essential factor in test 1. Next, I identify the number Q, which is 0, and this also belongs to Z. So it definitely passes the test number 1, where P is 5, which belongs to Z, and Q is 0, which belongs to Z. Now let's see the test number 2, which also needs to be passed before we justify 5 by 0 to be a rational number or not a rational number. So coming to P and Q, the test number 2 which says Q should not be equal to 0, but I clearly have Q equal to 0, and therefore this fails through the test number 2. This fails test number 2, and therefore it cannot be a rational number. Therefore 5 over 0 or any number denoted with the denominator being 0 cannot be a rational number, because 1 by 0 is undefined, which is infinity. It's how we understand the property. And therefore 5 by 0 is undefined, which tends to infinity, and it is not a rational number. Decided through the test number 1 and test number 2. Now let's take an example of a fraction which involves the roots to understand the rational numbers more deeply. For example, I have a number root 4 over root 9, which I have to decide on this being a rational number or not a rational number. So my question here is root 4 over root 9 a rational number? So let's justify this given problem through the test number 1 and the test number 2 before we decide for the number being a rational number. Now the given question is root 4 over root 9, which can be further simplified. As we have discussed even in the previous sessions, a number needs to be completely simplified before we justify for that number being a rational number or a natural number or a whole number or an integer or any other number in the branch of mathematics. So let's try to simplify this further, where root 4 clearly can be written as 2, because 2 square is 4 and root 9 is 3 square being 9. So the simplified form of root 4 over root 9 is 2 over 3, which now cannot be simplified further. So therefore I put this number 2 over 3 indirectly to both the tests, test number 1 and test number 2. Therefore here I get my P as 2 and my Q as 3, where in order to make the test number 1, I clearly see that P is equal to 2 is an integer and Q is equal to 3 is an integer. Therefore both P and Q pass the test number 1. Now let's try to see the test number 2. Clearly the test number 2 is about picking Q, where I got my value of Q, which is 3, and more further 3 is a non-zero number. Therefore this can never be equal to 0, and therefore equally Q equal to 3, which is not equal to 0, also is the pass of the test number 2 by the number root 4 over root 9. So this number, when simplified to 2 over 3, passes the test number 1 and also passes the test number 2, which makes us understand clearly that because of the two tests being passed, this number root 4 over root 9 is a rational number, and its simplified form being 2 over 3. So any number expressed in root or a non-root or a decimal or a non-decimal is justified through its most simplified form. The most simplified form here being 2 over 3, which is a rational number. Next, let's take an example of a decimal number and justify on whether the given number is a rational number or not a rational number. For example, I have is 4.956, which is a number which is expressed in decimal form up to 3 decimal places, and I want to justify this for a rational number. So my question here is 4.956 a rational number? Let's try to see based on the two tests applied for this basic definition. The given question is 4.956, and let's see if this can be expressed in the form P by Q, satisfying these two properties. Now, when I take the more simplified form, I clearly understand that any decimal to be tested for a rational number should be expressed in the non-decimal form, or should be converted into the non-decimal form. Therefore, 4.956, when it converts to the non-decimal place, it has its 3 zeros, which makes added to the denominator, so that this decimal 4.956 can be expressed as 4956 by 1000, the 3 zeros being counted on 1, 2 and 3 decimal places. Therefore, this, which can be expressed as 4956 by 1000, is the indirect simplified form of the given decimal 4.956. Now let's see if this passes through the two tests for a rational number. This is P, this is Q, and I have my P as 4956, and I have my Q, which is 1000 on the denominator. Test number 1, P and Q must be integers. Clearly, 4956 is an integer and 1000 is an integer. So I have my P and Q, which are integers. Therefore, the test number 1 is a pass. Next, coming to the test number 2, I have my Q, which is 1000 and which is not equal to 0, because 1000 can never be equal to 0, and therefore this also is a test number 2, which is a pass. Therefore, this number satisfies test 1 and test 2, thus this number being a rational number. Therefore, 4.956, which is the indirect representation of 4956 by 1000, must be a rational number. Q is how we understand the concept of rational number, understood through the two tests applied for the given problem. Now that we have understood about the rational numbers, let's try to see the relation of the set of rational numbers Q with natural numbers, whole numbers and integers. The relation says we have our natural numbers 1, 2, 3, 4, etc., and whole numbers, which is 0, 1, 2, 3, etc., and my set of integers, which is negative on this, and my rational numbers, which is all in the form P by Q, such that PQ belong to Z and Q not equal to 0. So clearly I understand that every natural number is a rational number, because if I take a number 7, which is a natural number, I can equally write this 7 as 7 over 1, which passes through the two tests. That is, this being P and this being Q, my P is 7 and Q is 7, Q is 1, and both belong, 7 and 1 belong to Z, set of integers, and therefore it passes the test number 1 for Q, and 1, which is the denominator, is not equal to 0. Therefore, every natural number 7 belonging to n can also be expressed in P by Q form, that is 7 by 1, and it becomes a rational number. Therefore, 7 belongs to n and 7 also belongs to Q. Therefore, I can say all natural numbers are part of the rational numbers, all integers are the part of rational numbers, and all whole numbers are part of the rational numbers. Is how we understand the concept of natural numbers, whole numbers, integers and Q. Is how we get the relation between n, w, z and Q, these three being part of Q. Q is bigger than n, w and z. Irrational numbers, the numbers which are not rational, the opposite of rational is irrational. So any number which is not a rational number is an irrational number. So any number which cannot be expressed in the form p by q, with p and q being integers and q not equal to 0, is an irrational number. I think you all get it now what an irrational number is. Irrational numbers is denoted by all real numbers except q, is how we denote the set of irrational numbers, and it is anything which is expressed in the form p by q such that q not equal to 0 minus p by q such that p, q are integers and q not equal to 0 is how we understand the irrational numbers. Let's try to see more better examples to understand what an irrational number is. Before we try to identify the irrational number, the most easiest concept is identify for the given number to be a rational or not a rational number. If the number is a rational number, it is not irrational. If the number is not a rational number, then it must be an irrational number, is how we understand. Let's start with an example problem. Is this an irrational number? Is the question out here. So root 5 over 9, let's test for this being a rational or an irrational number. For example, root 5 over 9 can be differentiated with the numerator being p and the denominator being q. Now clearly my p is root 5 and my q is 9. So let me put this to the two tests of the rational numbers. So with the test number 1, I clearly identify that q equal to 9 belongs to z, but p equal to root 5 cannot be an integer. Therefore, my p equal to root 5 does not belong to z. Therefore, this number root 5 over 9 fails the first test for a rational number. And therefore, root 5 over 9 does not belong to q. It is not a rational number. So this is not a rational number, so it is an irrational number. Therefore, root 5 9 over 9 is an irrational number denoted by all real numbers except q, r minus q, is how we justify an irrational number through the concept of q. Here being this is not a rational number, so obviously it must be an irrational number. Now let's try to take more examples to understand the irrational number more better. So let's take an example problem here which says with the question, is root 5 an irrational number? Or I take root 9 because I just want to have an example which is not an irrational number. So my question here is root 9 an irrational number? So here with this example, I clearly try to simplify this to a more simplified form where root 9 can be expressed as 3, which in turn can be expressed in the form p by q because I need to put through test number 1 and test number 2. So this can be expressed as 3 over 1 where my numerator is p and my denominator is q. Therefore, I have my p which is 3 and I have my q which is 1. And clearly these two pass through the test number 1 which belongs to z. P and q belong to z and it passes through test number 1. And test number 2, because q equal to 1 can never be equal to 0, therefore this passes through both the tests of the rational number. Therefore, I clearly understand root 9 is a rational number because root 9 indirectly expressed as 3 passes through the two tests. It is a rational number. and therefore root 9 cannot be an irrational number. A number which is rational can never be rational, and a number which is irrational can never be rational, and therefore root 9 being a rational number cannot be an irrational number. Is how we justify the irrationality of a number based on its rationality. To be continued with the examples, this session deals with the exceptional irrational numbers which we identify in the branch of mathematics. So let's see what these exceptional irrational numbers are out here. For example, I take the most popular mathematical symbol, which is pi. We all know that pi has a specific value, that is 3.14, and it continues forever without ending. Now this approximately we take as 22 by 7. So pi is approximately 22 over 7, but let's see if this is a rational or an irrational number. When I go with pi being 22 by 7, I clearly see that its p is 22 and its q is 7, so that my p is 22 in the numerator and my q is 7 in the denominator, and both belong to z. Therefore, this number pi, which is 22 over 7, passes through test number 1. And similarly, my denominator, which is q, is not equal to 0, is the test number 2, which the number 22 over 7 passes out in rationality. But when you see this clearly, because of the two tests, 22 by 7 is a rational number. Therefore, I need to assume that pi is a rational number. But this is an exceptional irrational number. Though it passes through the test of 22 over 7 being a q, cannot make pi as an irrational number. Cannot make it as a rational number, because pi is a mysterious number which has its value unending. Because we cannot predict, we only take the approximation of pi to 22 over 7, but not exactly equal to 22 over 7, and therefore this is not exactly a rational number. It is an exceptional irrational number. But pi is an exceptional irrational number. R minus q is how we identify the specific numbers in mathematics which are not accepted in irrational numbers. So it's an exceptional irrational number, pi. There's one more example which we can take, which is E. E is approximately 2.71, which is also an exceptional irrational number. So in the branch of mathematics, E and pi are exceptional irrational numbers, is how we identify in the branch of mathematics. Let's take one more example of an irrational number, which is very essential to understand the set of irrational numbers as compared to the rational numbers in the branch of mathematics. Non-terminating decimals. Let's justify for this to be a rational or an irrational number. What is a non-terminating decimal? A decimal which never stops, but it goes on repeating and repeating, is how we understand a non-terminating or a non-stopping decimal. For example, if I take a decimal in the form this seems to be never ending. As I form a sequence, this repeats never ending on and on till infinity. So such a decimal in the branch of mathematics is called a non-terminating or a non-stopping, never stopping decimal out here. So let's see if this can be a rational or an irrational number. To start with, the rational number with the two tests as we have already discussed in the session. Now, for the test, this should be expressed in the form p by q, but because it never ends out on the right, this cannot be expressed in the form p by q. X cannot be expressed in p by q form as the decimals never end. As the decimal part never ends, and therefore this, because it cannot be expressed in p by q form, therefore x cannot be a rational number. In order that it should be a rational number, the first essential thing is that it should be expressed in the form p by q, with test 1 and test 2 being followed with that. But because it cannot be expressed in p by q form, x cannot be a rational number. Therefore, any terminating decimal can never be a rational number. A terminating decimal is always an irrational number, is how we identify the property out here. So the outcome is that the terminating decimal belongs to R minus Q, is how I understand the property of the terminating decimal being an irrational number always, can never be a rational number. Now the last set of numbers in the field of mathematics in here is real numbers. Starting with natural numbers, we proceeded with natural numbers to whole numbers to integers, integers to rational numbers to irrational numbers, and finally from irrational numbers to the real numbers. So real numbers are generally denoted by R, and it has the same definition as that of rational numbers, with only the test number 2 absent out here, with test number 1 absent out here. So for example, I have this R denoted by capital R. My real numbers is defined as P over Q such that Q not equal to 0. So I clearly understand that in the absence of test 1, I don't have the condition for the numerator and denominator to be integers, provided the denominator should never be equal to 0 in any of the numbers in the number system, because 1 by 0 is infinity, undefined. So real numbers is this: P by Q such that Q not equal to 0, irrespective of the condition for P and Q being any integer or a non-integer. For example, I have a question which says, is root 3 over root 7 a real number? So let's see if this is a real number. Root 3 over root 7, which can be written in the form P by Q, clearly states that Q is equal to root 7 can never be equal to 0, because root 7 is a non-zero irrational number. Therefore, Q not equal to 0 is the test, which is the only test which needs to be passed for a number being a real number. Now this test is passed, therefore root 3 over root 7 is a real number. But this cannot be a rational number because P and Q are not integers. Root 3 over root 7 is not a rational number, is how we understand the difference between a real number and a rational number. A rational number, we have the numerator and denominator to be integers, but in real number, the only condition being denominator should never be equal to 0. So root 3 over root 7 is a real number, but root 3 over root 7 is not a rational number, is how we understand the concept. Instead, root 3 over root 7 is an irrational number and a real number, but not a rational number. Now let's take another example to see if the given number in the question is a real number or not a real number. For example, I have the question, is 7 by 0 a real number? Is the question out here. So let's pick the given number 7 over 0, as clearly I see that it is in the form P by Q, with Q being tested for the real number. Now clearly I have Q equal to 0, which fails with the test that Q should not be equal to 0. Therefore, this number which fails the test of a real number clearly states that 7 over 0 can never be a real number. Is how we understand the real number is all sets of numbers with only the exception to those numbers whose denominator is 0. Is how we understand the set of real numbers. Now let's see the relation of 0 in the denominator connected with R, Q, R minus Q, Z, W and N. So as we have discussed in each of the examples, we have identified a very important note that for any number where the denominator is 0 can never be a real number, can never be an irrational number, can never be a rational number, can never be an integer, or can never be a whole number, or can never be an integer. So the branch of mathematics does not accept a number with denominator 0 in any of its number system. It's an exception for the number system itself, simply because 1 by 0 is infinity, and which is undefined, is the reason why this is an exception to the number system. Now that we have discussed about the different types of set of numbers in the number system, let's try to compare all of the numbers, the set of real numbers, set of irrational numbers, set of rational numbers, set of integers, set of whole numbers and set of natural numbers combined together, and the relation of each to the other. Now this is more important in understanding through the Venn diagrammatic representation. So let's take the Venn diagrammatic representation to understand each of the sets. Now we have the set of real numbers denoted by R, and I have the set of rational numbers denoted by Q, and I have the set of integers denoted by Z, and I have set of whole numbers denoted by W, and set of natural numbers denoted by N. Is how we denote through the circular or the Venn diagrammatic representation. So here I clearly understand that the bigger circle or the bigger set is R. So this is the mother of all the sets. So real numbers is what through which all the numbers come out, and the least set is natural numbers. So this makes me clearly understand that all rational numbers which are inside the circle of the real numbers makes me clearly understand that all rational numbers are part of real numbers. So every irrational number is a real number. Every integer is a rational number, and every integer is a real number. Every whole number is an integer, every whole number is a rational number, or every whole number is a real number. Similarly, every natural number is a whole number, every natural number is a real number, every natural number is a rational number. But if you go the other way, every integer is not a natural number, because Z is not inside N, but N is inside Z. So every natural number is an integer, but every integer is not a natural number. Similarly, every rational number is a real number, but every real number is not a rational number, because R is outside Q and Q is inside R, is how we can easily analyze the properties using the simple diagrammatic representation N, W, Z, Q and R, which makes us understand whether the number is a subset of each of it. The other way of representing this Venn diagrammatic or the circular representation is that N is part of W and W is part of Z and Z is part of Q and Q is part of R, is how we understand the relation between each of them. And more importantly, this region between the rational number and the real numbers is irrational numbers, which is represented here. So this region represents all the irrational numbers which lie between the rational and real in this region of, is how we understand the different set of numbers in the branch of mathematics which are related, interlinked to each other through this Venn diagrammatic representation. Now that we have discussed about different types of number systems in the branch of mathematics, the real numbers, the rational numbers, irrational, integers, whole numbers and natural numbers, now let's see how we can represent the irrational numbers which are not the exact numbers on the number line, the real number line. Let's recap the irrational numbers which we have discussed in the previous sessions. Irrational numbers, as we have discussed, are the elements which are written in the form R minus Q. So all numbers which are not rational or which cannot be expressed in the form P by Q, failing both the tests, PQ belonging to Z and Q not equal to 0, is how we define irrational numbers. So let's see how these irrational numbers can be exactly located on the number line through the exact distances. For example, I take the irrational number root 2, which is clearly an irrational number. Now, when I convert this into the decimal representation, we know that root 2 is approximately 1.414 and dash dash. Now, because this is not an exact number, even in its decimal place, we will try to use some geometrical construction methods to represent root 2 on the number line through the exact distance. Let's see how we can do this. Before we just try to construct root 2 on a number line, let's try to recap with some geometrical constructions which are useful in construction of root 2 on the number line. For example, I take a square of side 1 unit. So here I have a square of side 1 unit with all sides being equal with 1 unit on each side. Now here I try to extend the diagonal from one corner to the other corner. So we know that this diagonal forms the hypotenuse for one of the right angled triangle taken on either side of the diagonal for the square. Now this being a right angled triangle, let me say this is A, B and C. So ABC forms a right angled triangle, right angled at B, with AB equals 1 unit and BC equals 1 unit. Therefore, by using Pythagoras theorem, I have AB square plus BC square equals AC square, and which on further representation of the given values gives me 1 square plus 1 square is equals AC square, using Pythagoras theorem. Now when I further simplify this, I get this to be AC square equals 1 square, which is 1, and 1 square, which is 1, when on further adding up gives me AC square equals 2. That implies my length AC, which is the diagonal of the square, equals root of 2, is how I get the root 2 out of 1 unit of the square. So this dimension of the diagonal being root 2 is what we utilize in representation of root 2, which is an irrational number, on the number line. So let's see how we can just take this further into geometrically constructing root 2 on the number line. Let me take the number line before we construct root 2 on the number line, or representation of root 2 on the number line. So here is the real number line, which extends from minus infinity to plus infinity, with all the points on this line being the numbers of the real numbers, or the real numbers of the number system. So here I have the real number line, which is represented through the line and called the number line, and here I have exactly in between the neutral 0, from where on the right side you have all positive values, on the left side it's all negative values. So let me just proceed with the right side of the values, which is 0, 1, and next comes 2 and 3, and so on and so forth till infinity on the right. Similarly, on the left I have negative 1, negative 2, negative 3, and etc. onto the negative side of the infinity. Now let's try to see how we can construct root 2 on this number line, using the previous discussion of the square, which gives me with the dimension of 1 unit, and its diagonal, which gives me the distance of root 2. So let's see how this can be transferred into the number line to get the same root 2 on the number line. So in order to do that, I need to have this diagonal placed on this number line, which is possible by constructing a square of 1 unit. So here is 1 unit, so I construct a square of 1 unit on each side in this form. So once I construct a square of 1 unit starting from 0 to 1, that is a square being built on the number line, I try to join this diagonal from one end to the other end. Let me just mark this as A. Now OA is the diagonal for this square, which we know indirectly is root 2. Therefore, I just transform this dimension into root 2 out here. So I get to be OA equals root 2 units, using the concept of the square, which we have already discussed in the session. Now with this root 2 units, now I take a compass and just point it at O and put the compass at A and just draw an arc. So when an arc is cut, I just get an arc which cuts the number line, indirectly stating that this forms a circle with same radius. Therefore, the radius of root 2 units made by the compass is nothing but the radius of the same root 2 units as made by the compass on the number line, and thus we get the distance root 2 out of the square diagonal in this manner. So when we would like to construct root 2 on the number line, we try to first construct a square of 1 unit on the number line from 0 to 1 unit, and then take its diagonal, measure the diagonal with the compass, then draw an arc such that the arc cuts the number line. And the point where the arc cuts the number line, I denote it with B, and OB is root 2 for sure, because the radius is the same for any part of the circle from its fixed center. Therefore, my OB as constructed from the arc is also root 2 units, because it is the same radii, the same radius concept, and therefore my distance on the number line from O to B is what is the distance, which is an irrational number, root 2, which can be represented on the number line in this manner of constructing through the geometrical square diagonal. Next, let's see how to represent the irrational number root 3 on the number line. Of course, root 3 has the value which is 1.732 and so on and so forth in its decimal representation. So this value root 3, an irrational number root 3, I would like to represent on the number line, just like root 2, how it can be represented on the number line. So let's see what geometrical concept can be used in case of root 3 to construct on the real number line. So here I have, say for example, I take a right angled triangle and I have this to be an isosceles right angled triangle, 1 unit and 1 unit, and therefore of course it's an isosceles. So these two sides being equal, it is an isosceles right angled triangle such that the two sides are 1 unit each. Then obviously by using Pythagoras theorem we know that the hypotenuse is root 2 units, as we have seen in the previous session of the diagonal of a square. So this being root 2 units, let's see how we can develop root 3 using this root 2. Imagine I take the point OAB and I try to take the point O and I construct a line perpendicular to OA and passing through A. That is, I draw a line through A perpendicular to OA, the side OA of the triangle OAB. So here I construct exactly with the distance being 1 unit. So this is exactly same as this of 1 unit. So here I mark this to be C. So C is the point which is exactly 1 unit from A and which is perpendicular to the side, the hypotenuse OA of the right angled triangle. So now I have the side CA which is 1 unit and I have the side OA which is root 2 units, as we can clearly see through the diagram. Now with this, let me join C to O. Say I just join C to O out here. Now let's try to calculate the dimensions of the side OC which is joined for this triangle ACO. Now let me just focus on triangle OAC and let's see what we witness from this triangle OAC. As we can see the triangle OAC, we see that AC is 1 unit and OA clearly is root 2 units, is what we have from these two dimensions. And clearly this being 90 degrees, it's a right angled triangle and therefore we have the Pythagoras theorem which comes into existence. Triangle OAC is a right angled triangle and therefore this being a right angled triangle, we are going to focus on the Pythagoras theorem. So let's see what happens with Pythagoras theorem applied out here. So we know that in right angled triangle OAC, the hypotenuse OC square is sum of squares of other two sides, that is OA square plus AC square. And then when I further substitute the values, I get this to be OC square is equal to OA, which is root 2 whole square, and AC, which is 1 whole square, which on further simplification gives root 2 whole square. We know that root x into root x, which is root x whole square, is x, because the root and the square both get cancelled, and therefore I get x. Similarly, root 2 times root 2, which is root 2 square, is 2, and 1 square, which is 1, which is finally 2 plus 1, and that is equal to 3. Now in this case, when I further simplify this, I get this to be OC square is 3. That implies my dimension OC is square root of 3. When the square comes out here, it comes out as root of 3 units. So this is how I get the dimension of OC. Constructing or locating root 3 on number line, we use this geometrical concept of the triangle, and finally we get the distance OC, which is root 3 units. And this is how we locate this on the number line. Is how we just understand geometrical construction of root 3 on the number line using the right angle triangle and most importantly the Pythagoras theorem of the right angled triangle. Now let's take the real number line and construct root 3 or locate root 3 on that real number line. So I have the real number line out here, which extends itself from minus infinity to plus infinity is how this extends. And here we have the neutral 0 through which on the right hand side they extend up to 1, 2, 3, 4 and so on and so forth, and the left hand side has minus 1, minus 2, minus 3, etc. Now on this real number line I take a right angle triangle, as we have seen that root 3 was constructed through an isosceles right angle triangle 1, 1, root 2, 1, and this finally gives me root 3. So I'm going to use this concept of the geometrical triangles on the number line, and finally this distance is taken as the radius arc, and when we draw through the compass it cuts the number line exactly at root 3 units is the concept which we are going to use in here. So when I take isosceles right angle triangle from 0 to 1 with 1 unit each, I get this to be 1 and 1, and this extends in the diagonal with this to be root 2. And finally from here I take a compass, I drop the perpendicular, and then I just get this to be exactly 1 unit. I measure the length 1 unit and cut an arc, and then I get a triangle with the dimension of root 3. So here is, say for example, OA with length root 3 units. So I have the length OA, which is root 3 units, as constructed through the Pythagoras theorem and discussed in the previous session. I take the compass, put the center at O, and just draw an arc from A, and I get this to be an arc which extends out here, and therefore I get the radius root 3, which is also the radius out here on the number line. So this distance is root 3 units, which cuts, say, at the point B. So my OB on the number line is root 3 units, which I construct on the number line. On real number line, my length OB is root 3 units, is how I locate the irrational numbers through the geometrical processes on the number line. Rational numbers on real number line. Now that we have seen the process of locating root 2, root 3 on the number line, what about root 5, root 6, root 7, root 8, or other square roots which can be represented on the number line? Is it that only root 2 and root 3 are the only numbers which can be represented on the number line? Or are there every irrational number which can be represented on the real number line is the biggest question out here. So let's see, investigating on further irrational numbers, let's see a consecutive pattern or a process which can be identified on construction of the irrational numbers using the geometrical concepts. So here my session today is about locating square root of n on the number line, of course the real number line. So let's start with 1. Let me just take O and A, and here I have A, and this is 1 unit, and then I have this to be also 1 unit with 90 degrees. Then from here, when I take this to be B, I have OB clearly, which is root 2 from Pythagoras theorem. So this is 1 unit and this is 1 unit, so this is root 2. Now using root 2 and the distance of 1 unit, I get this to be again a Pythagoras theorem, which gives me root 3. Again, taking this as C, OC is root 3, and next I construct a perpendicular from at C and at a distance of 1 unit, then what I join here will be root 4. Let's see how it comes. So when this distance OC is root 3, and say my distance from D to C is 1 unit, and then this forms a right angle triangle ODC, in triangle ODC, which is a right angle triangle, I have the Pythagoras theorem which says OD square is equal to OC square plus CD square. Now we know that OD square is what we need to find, with OC being root 2. So I have this to be root 3 square plus CD square, which is 1 square. Now this root 3 square is 3 and 1 square is 1. With square root and root gets cancelled with the square. I get this to be 4. Then I get my OD, which is root 4. Of course, root 4 is 2. So my distance OD is root 4, through which I again proceed in the same process, so that I take from D a perpendicular of 1 unit which cuts D exactly 90 degrees. And here, this being 1 unit, let me mark this with E and then join OE. Let me again take triangle ODE. In triangle ODE, which is a right angle triangle, right angled at D, I have again the Pythagoras theorem, which plays a vital role. So using the Pythagoras theorem, the hypotenuse OE square will be equal to sum of squares of other two sides, which is OD square plus DE square. Now I have my OD, which is calculated as root 4 or 2. So OD, which is root 4 or 2 square, plus DE, which is 1 of square, gives me 4 plus 1, which is 5. Therefore, OE square is 5, implies my length OE is root 5. This is how I identify that as I construct the 1 unit perpendicular length on through the different sides of the polygon, I get the different distances from O, which are nothing but the roots in consecutive integers or roots in consecutive natural numbers. So I have root 1, this can also be taken as root 1, this as root 2, root 3, root 4, and then finally this comes out to be root 5. So this distance OE is root 5 units. So in order to construct the root 6, we again take 1 unit perpendicular from E exactly with a length of 1 unit, join the dimension, we get root 6, root 7, root 8, root 9. So one important thing what we note is, in order to find root 5, we need the length root 4. In order to find the length root 4, we need the length root 3. In order to find length root 3, we need the length root 2. In order to find the length root 2, we need the length 1. So it all starts from 1 unit. Therefore, in order to find the length root n, we need the length root n minus 1, 1 short of unit. So therefore, I come with the learning outcome. In order to find the length root n, I need to find the length this first. So in order that I find the length root 5, I need to first find the length root 4 before I find the length root 5, or locate root 5 on the real number line. So its consecutive or its preceding root number should be identified before we locate the next coming natural number under the root. So in order to find the length root n, I need to find the length root n minus 1 first, is what I make the learning outcome out in this session. So finally, root n for all n belonging to z plus can be represented on the real number line. If here being n belongs to z plus is how we identify the location of irrational number on the real number line. So the square root spiral, which we call this, is the useful tool in identifying the irrational number on the real number line. So number line can have the rational numbers being located using this square spiral. Now let's see how a non-terminating decimal be expressed in p by q form. Or is it possible that a non-terminating decimal be expressed in p by q form, that is in a rational form such that p and q belong to z and q not equal to 0. So I want to express a non-terminating, a never-ending decimal number into a decimal in the p by q form, a rational number. So let's see how we can just do that, or is it possible to do that or not. For example, I take a non-terminating decimal denoted by x for 0.3 bar. Now the bar is what we know, which we have learnt in the lower classes, to be a repeating number which is denoted so on and so forth with a bar. So bar indicates that 3 repeats till infinite times. So 0.3 bar implies this can be indirectly written as 0.33333, so on and so forth. Now let's see if this number, which is never ending or non-terminating or ever recurring decimal, which can be expressed in the rational form p by q, with p and q belonging to z and q not equal to 0. So let's see if it's possible. So x is 0.3 bar, which can be written as 0.333 and so on and so forth till infinity. Then I multiply 10 on both sides so that I get this to be x times 10 is 0.333, which is also equally multiplied with 10 on both sides. So this equation is multiplied with 10 on both sides. So x times 10 is 10x, and 0.333 so on and so forth times 10 is 3.333, because this 0 makes the decimal shift to the right, and 0 vanishes when the decimal shifts to the right as 3.333, so on and so forth. So I have two equations here, equation 1 and equation 2. So I have these two equations which I'm going to take out here. So with equation 2 being 10x equals 3.333, so on and so forth, and my equation 1, which is 0.33, so on and so forth, I try to subtract the two equations so that this, on subtracting, changes the sign, and I get 10x minus x, which is 9x, and 3.333, so on and so forth, minus 0.333, so on and so forth, will exactly give me 3. The subtraction will make this as 3.00 and so on and so forth, because 3 minus 0 is 3, 3 minus 3 is 0, 3 minus 3 is 0, 3 minus 3 is 0, and so on and so forth, all zeros till infinite times. Therefore, this on further simplification reduces to 9x equals 3, which by taking the constant to the right gives me x equals 3 over 9, which is 3 1s, 3 3s. Therefore, x is 1 over 3. Therefore, my x, which is 0.3 bar, can be written as 1 by 3. So I finally understand that x, which was 0.3 bar or which was 0.333, so on until infinity, can be expressed in the form p by q with P being 1 and Q being 3, and both P and Q belong to Z and Q not equal to 0. Therefore, it is possible that every non-terminating decimal can be expressed in the P by Q form, the rational form, with two tests: test 1, PQ belonging to Z, test 2, Q not equal to 0. Now let's see what if the non-terminating decimal or the recurring decimal is with two decimal places. In the previous session, we have seen a number which has one decimal place, 0.3 bar. Suppose I have the bar for 2 digits. Let's see how we can construct, or how we can convert that into rational form. Or is it possible or it is not possible for construction, is what we're going to investigate in this session. For example, I take my value of x, which is 2.69 bar. Suppose my bar is for 2 digits, then the only thing I do is I just try to expand this, repeating the bar all the times. And the secret behind this is to shift this decimal not by one place but to 2 places, because it is the repeating number which is taken into account every time we try to convert the non-terminating decimal into P by Q form. So I have this to be the number which repeats is after every 2 digits. Therefore, the decimal has to shift twice on the right, which is possible by multiplying 100 on both sides. Because if I multiply 10, the digit moves only 1 unit shift to the right. But if I multiply with 100, the 2 zeros make the decimal shift 2 units to the right. And therefore, when I multiply x with 100 on both sides, I get this to be this times of 100, and which on further simplification gives 100x equals 269.6969, and so on and so forth. And my original x, which is this, converts to be x equals 2.69696969. The reason behind putting the decimals same is that when we subtract, all the decimals should get vanished, and therefore in order to make the decimals equal, the only possibility is by multiplying 100 on both sides, so that here I can subtract so that all the decimal values vanish to 0. So after this, my next step is to subtract, so that 100x minus x is 99x, and 269 minus 2 is 267.69000000, and so on and so forth, is how it vanishes in the decimal part when we subtract through multiplying 100 on both sides. So I get this to be x equals 267 by 99 is how we get, and I can further simplify this to be 3 8s are 24, 3 9s are, and 3 33s. Therefore, this most simplified answer for this is 89 over 33. Therefore, my representation of 2.69 bar, which is a non-terminating decimal which repeats 696969, can be written in the rational form as 89 over 33. P and Q both belonging to integers and Q not equal to 0 is how I understand the connection of the non-terminating decimal, which is possible to be converted to P by Q form. Similarly, if I have a 3-digit repeating number, say for example I have x equals 1.413 bar, then I have the 3 digits which repeat on and on. because there are 3 digits repeating, the concept of multiplying by 100 for 2 digits shifts to multiplying by 1000 on both sides, because 3 zeros make 3 digits shifted by the decimal to the right. This is how we understand accordingly through the number of digits which have the bar existing, the number of zeros which we multiply on both sides, is how we understand the tricky concept. So now that we have seen representing the irrational numbers root 2, root 3, etc. on the number line, let's try to see if any real number can be represented on the number line in approximation exactly where it has to be located. So here my session is about representing real numbers on the number line. For example, I take the number x equals 2.6. Now it is very easy to locate the number x equal 2.6. Or say for example, I take x equals 3.7. I find 3.7 to be easily located on the number line, because if I have the number line with minus infinity, plus infinity, 0, 1, 2, 3 and 4, etc., then I find 3.7 approximately here. So how do we get this to be approximately on the right side is how we're going to discuss in the number line. So this representation of 3.7 is just because if I take a second number line which is extended which is zoomed out for between 3 and 4, I see that between 3 and 4 I have 10 different scales: 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So I get this to be 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.9. So between 3 and 4, I again subdivide the scale into 10 units, breaking up at each unit being 3.1, 3.2, 3.3, 4, 5, 6, 7, 8, 9 and 10. Is how I get this point, exactly the 3.7, which is located by using the second number line out here. So my 3.7 is located through subdividing the scale between 3 and 4 units into re-subdividing again into 10 different units, so that I can exactly locate 3.7 on the number line. Say I continue this with the number x1, which is 3.74. I would like to locate the number 3.74, which is again more approximate value than 3.7. So what do I do with this number line? I start with the first number line between 3 and 4 somewhere out here. Again I subdivide. I get between 3 and 4 10 different units, and again 3.74 lies between 3.73 and 3.75. The value on the left of 3.74 is 3.73 and the value on the right of 3.74 is 3.75. So what do? I pick between, and also this value is between 3.7 and 3.8. So this value of 3.74 lies in the region between 3.7 and 3.8. So this is the region where this value lies. Therefore, I try to again break up this interval into 10 subdivided intervals. Now let's see how the number 3.74 up to 2 decimal places be represented on the number line exactly through its subdivided interval. Now as we know that 3.74 lies between 3.7 and 3.8 in this interval of, we'll try to make a number line between 3.7 and 3.8 subdivided again into 10 different intervals. So we get this to be minus infinity to plus infinity of I take 3.7 and 3.8 and I subdivide this into 10 different intervals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get this to be 3.71, 3.72, 3.73, 3.74, 3.75, 76, 77, 78, 79, and this is finally 3.8. So my 3.74 can clearly be identified to be out here, which is 3.74. Is how we understand the subdividing of intervals through which we can reduce or zoom in and zoom out the real number line accordingly as the number of decimals increase or decrease. For example, I continue further with the new number x2, which is 3.742. Then I have my third decimal, which is 2, and I clearly have this number lying between 3.74 and 3.75. So I try to locate the region between 3.74 and 3.75, and I make a new number line breaking up with this. And I have my 3.74 divided into different subintervals 1, 2, 3, 4, 5, 6, 7, 8, 9, and then finally I get to be with 10th interval, which is 3.75. Now 3.741 lies here and 3.742 lies here. 743, 745, 746, 747, 748, 749, and 3.75 is what we get out here. Therefore, the number 3.742 is said to be exactly lying out here. So here is what I identify, and proceeding similarly, as the number of decimals increase, the number of number lines get zoomed in and zoomed out, and where again the subdivided intervals can make me locate exactly the number fixed located on the real number line. Therefore, finally, the learning outcome is that every real number can be represented on the number line, however big the number of decimals are. The successive magnification of the given decimals through the successive magnification of the number line will finally give us, through the first magnification, which gives me the value 3.7, the second magnification, which gives me the value 3.74, and my third magnification, which gives me the value 3.742, is how I identify that through different successive magnifications I can visualize and locate the given decimal values on the real number line. Successive magnification is possible for identifying the real numbers on the number line. Now let's see the different types of operations which are applicable in real numbers, mostly the rational numbers and irrational numbers, which play a vital role in simplification process. For example, I have two real numbers. Say my x is root 3 plus root 2 and my y is root 3 minus root 2, and I wanted to know clearly x is an irrational number and my y is also an irrational number. So now let's see what the product would yield in its simplification through operations using real number properties. So when I multiply the two irrational numbers x times y, I find that x being root 3 plus root 2 is substituted for x, and root 3 minus root 2 is substituted for y respectively in the product. Now clearly I identify that this is in the form a plus b times a minus b, which equals a square minus b square, as learnt in the lower classes. So a plus b times a minus b is a square minus b square. Therefore, root 3 plus root 2 times root 3 minus root 2 is root 3 square minus root 2 square, is what we get in the form of the product. So root and squares cancel. So root 3 square is 3 and root 2 whole square is 2. Therefore, my product xy is 3 minus 2, which is 1. Now clearly I identify that for two irrational numbers when multiplied is giving me a rational number. Moreover, it's an integer or a natural number or a whole number. So the product of two irrational numbers can yield a rational number, is how we identify the concept of rational numbers connected. Therefore, my outcome is product of two irrational numbers can yield a rational number. Therefore, product of two irrational numbers can yield a rational number, but it is not always true, because it is not always possible that two irrational numbers can yield a rational number. Only sometimes when the formulas can be exactly applied, is how we understand the concept of product of two rational numbers yielding a rational number. What about two rational numbers when multiplied? The product of two rational numbers cannot yield an irrational number, because it is its own respective rational numbers when multiplied which always gives a rational number. But the only exception is two irrational numbers when multiplied may give a rational number, but two rational numbers when multiplied always gives a new rational number. Now let's see how a number root x for any x belonging to real numbers be represented on a number line. So I would like to represent root x on a number line for x being a positive real number. Of course, roots are defined only for positive real numbers. Now that in the previous session we have discussed about locating root 2, root 3, root 4, root 5, etc. using the square root diagram or the square root construction of a polygon, through which we can locate only using the geometrical concept for integers. If you have a fraction, say I have something like root of 4.9, which I would like to locate on the number line, then it becomes quite difficult. Or how I can measure the length, this root 4.9 on the distance, is what is the biggest challenge out here. Therefore, let's see in today's session about how we can represent a root of a real number on a number line. So imagine before this, we need to go through some construction process to understand the representation more better. For example, I take this to be the distance AB, which is some x units. Imagine my distance AB is x units, and from B, the line AB is extended further one more unit, so that the distance BC is 1 unit. So I have here AB is x units and BC is 1 unit, is what we get with the complete number line from A to C. Now let me say the midpoint of AC is at O. So here is the midpoint of the line AC, which exactly is at O. So O is the midpoint of the line segment AC, through which AO is equal to OC. Now, let's try to construct the different key factors in understanding on how we can identify root of x using the number line. So for example, I take the length OC or OA and then try to construct a semicircle using the radius from compass O to A. So with radius as OA, here is my semicircle, the radius being OA. Now let me just draw a perpendicular from B so that it cuts 90 degrees and passing through B. So I drop a perpendicular onto B which cuts the semicircle, say at some point D. So D is the point where the line, the perpendicular line passing through B cuts the semicircle at D. Let me join OD. So here I have a right angled triangle OBD through this construction. Now how do I measure the distance OB? I would like to measure the distance OB. So I see clearly that OB is OC minus BC. So the distance OB is the entire radius minus this, which gives me the distance OB. Therefore, my OC is the radius which I need to find out here. So let's see what will be the radius OC. Now because my diameter AC is x plus 1, because it accounts to x and 1 unit, my whole distance AC is x plus 1. So x plus 1 being the diameter, the radius OC is exactly half of AC, and therefore it is exactly half of x plus 1, because AC is already substituted to be x plus 1, is already simplified to be x plus 1. Therefore my OC is x plus 1 by 2. So I just substitute this to be x plus 1 by 2 minus BC, which is 1. Substituting for OC and BC respectively, I get this on further simplification to be x plus 1 minus 2 by 2, and this gives me x minus 1 by 2. Therefore my distance OB is x minus 1 by 2. Therefore my distance OB is x minus 1 by 2, and my distance OD is nothing but distance OA, which is already identified to be half of this. So OC is nothing but OA, and the distance OD is equal to distance OA, which is already identified to be x plus 1 by 2, because this and this and this are the radius. The radii of the circle are equal. Therefore my OB is x minus 1 by 2, and my OD, which is simplified out here, is x plus 1 by 2. Now I have OB and OD through which I am going to find the length BD. To find the length BD, we are going to use the triangle, right angle triangle OBD, and then through Pythagoras theorem, let's try to find the length BD. So to find BD, I take right angled triangle OBD, in which I have OD square equals OB square plus BD square using the Pythagoras theorem. Now OD square is x plus 1 by 2 whole square, because I have OD which is substituted out here. My OB is x minus 1 by 2 whole square, which on substitution gives me this, plus BD square. So I take BD square to the left and all the terms to the right and simplify, so that I get this to be BD square equals x plus 1 by 2 whole square minus x minus 1 by 2 whole square. Now this on further expansion gives me x plus 1 whole square by 4 minus x minus 1 whole square by 4. To be continued it has x plus 1 whole square by 4 minus x minus 1 whole square by 4, which can be simplified using the LCM. Therefore, I get this to be bd square equals x plus 1 whole square minus x minus 1 whole square by 4, which on further simplification gives a square plus 2ab plus b square minus a square minus 2ab plus b square by 4, which on further simplification gives x square plus 2x plus 1 minus x square plus 2x minus 1 whole by 4. This gets cancelled and 1 gets cancelled, and we have 4x by 4, which is x. Therefore, my BD square is x, which implies the length BD is root x units. So my length BD is root x units is how we construct using this geometrical process. So finally I get my length BD, which is root x units. So using this BD, finally I try to identify that using any real number x on this dimension of AB, I can construct root of that real number through this distance. The derived formula, which already gives the length BD, is indirectly the square root of this number, is how we identify the geometrical process out here. Let's see how the root x concept can be applied in real life for constructing the root of 5.3, which is an irrational number without an integer. So square root diagram doesn't help us, the spiral square root doesn't help us in the process. So let's use the previous concept of constructing through root x from x. Now as I take the given number, which is root 5.3, which has to be located on the number line, I clearly find that the x value out here is 5.3 from the root x. So we first pick the value of x, and then in step 1 of the construction, we take the distance 5.3 out here. So let AB be the base constructed with exactly 5.3 units. It can be centimeters, it can be meters, but take the measurement of 5.3 as the base of AB. Extend this line so that we take the unit, the distance of 1 unit, and cut on the number line so that this acts as 1 unit. So this line segment AC has 2 segments, AB and BC, with the length AB equals 5.3 units and the length BC equals 1 unit. So which totally accounts to 6.3 units. Now I have the AC, which is AB plus BC, and 5.3 plus 1, which is 6.3 units, is the diameter of the semicircle. Now using this complete line segment, I will try to find the midpoint of AC. So midpoint of AC, which I mark as O, is assumed to be the center of the circle, and let's see what is the distance AO or OC. Is O, and AO equals OC, which is half of AC, because the distance this is half of the entire length, and AC being 6.3 will be half of 6.3, which is 2 3s are 6, 2 1s are 2, 2 5s 10. So this is 3.15 units. So my AO is 3.15 units, and the distance AO, which is 3.15 units, is cut. Take the compass at A and cut a distance of 3.15 units, and then we get the midpoint. Or take the scale and mark exactly the middle point. There are different ways through which you can do through the perpendicular bisector. which also gives us exactly the midpoint. Take more than half, cut an arc, cut an arc, cut an arc, cut an arc, and we get the midpoint out here for the line AC by fixing at A and C and cutting the arcs. So once we get the midpoint O, I assume that my distance AO is nothing but the distance OC, the radii, and then that is equal to 3.15 units. Now take the center and draw a semicircle with OA as the radius. So the next construction is to draw a semicircle in this manner. So once a semicircle is drawn through O with the radius as OC or OA, I get a semicircle in this manner. Now from here, the next step is to drop a perpendicular from B. So put the protractor at B and make a 90 degrees through the line AC. So with the base as AC and angled at B, I get 90 degrees, which is extended to cut the circle at D. So here I have my distance D, which is from B and which cuts the semicircle exactly out there. So this is how I get the point D, by extending the line to cut the semicircle. Now once I get this, it's all about joining D. And the property which we have done in the previous session is that if this is X, this will be root X. So if this distance is 5.3 units, then the distance which you cut at semicircle from B will obviously be root 5.3 units, is what we have derived in the previous session. This length being X, this length gives us root X, is what is derived. And hence, this length being 5.3 units has to obviously give us this distance BD, root 5.3 units. And hence, this distance, again taken on the number line, will cut from 0, take this distance and cut here, then I get this to be root 5.3 unit. And that is how we can mark it on the number line, where root 5.3 units, which is the measure of this length, can be represented on any number line. So root X for X belonging to R plus can be represented on a number line using the semicircle geometrical concept properties. Now next, let's see how to rationalize the part of irrational numbers. So the concept here is rationalizing the irrational numbers. Part of. Let's see how this can be done out there. So for example, I have a number 3 by root 12. And I would like to rationalize this denominator because my denominator is an irrational number which I would like to rationalize. So in order that I rationalize, I understand that its root has to be removed. Rationalizing the root is possible only when the root vanishes. Therefore, in order that root 12 has to vanish, let's try to see how this is possible. It's very simple, because when you have the number 3 by root 12, I can simply rationalize the denominator by multiplying and dividing the same rational number besides the given number. So here is the root 12, so I multiply and equally divide so that it doesn't disturb the justification of the mathematical value out there. So once the root 12 is multiplied and divided, I get this to be 3 times root 12, which is 3 root 12, and root 12 times root 12 is already known with the property root x times root x is root x whole square, which is x, and therefore root 12 times root 12 must be 12, and therefore this can be simplified as 3 1s 3 4s root 12 by 4. This can also be further simplified by taking root 12, which is 4 times 3, and by 4. so that this can be split as root 4 times root 3 by 4, because root AB is root A times root B. Every factor can be split in the root provided it is in multiplication. Root of A plus B is not equal to root A plus root B. The splitting of roots is possible only in division and multiplication. So I have root 4, which is 2 times this by 4, which can be further simplified as 2 once and twice, so that the final answer is root 3 over 2. So interestingly, the irrational number which was in the denominator jumps to the numerator. So we have now an irrational number in the numerator, but there is no irrational number in the denominator. This is how we rationalize through either the numerator or the denominator, depending on the question given. Rationalizing the numerator and the denominator is very much possible, as witnessed with this example problem. Let's see one more example through which we understand the rationalizing concept of an irrational number more better and more stronger. For example, I have my x, which is 1 by root 11 minus root 9, or I have this 2 by root 11 minus root 9. And I clearly see that the denominator has irrational numbers and the numerator has strictly a rational number. So my question out here is, how do we rationalize the denominator, which is irrational presently? So let's see how we can rationalize the denominator out here. So in order that I rationalize this denominator, the concept in case of two added or subtracted numbers is that I multiply and divide the same number with opposite sign in between. That is, when I have 2 by root 11 minus root 9, then I multiply and divide with the same irrational numbers but with opposite sign. If I have minus out here in the given question, I have plus, which I multiply and divide. If I have plus in the given question, I put the opposite sign minus in the numerator and denominator. Is how we understand the general rule which applies for any problem where the denominator or numerator is rationalized in this format. So I multiply and divide with this, which gives me 2 times of root 11 plus root 9 by root 11 minus root 9 times root 11 plus root 9 is how we get it. Now clearly I see here that this is root 11 plus root 9 by, this is clearly in the form a minus b into a plus b, which we know through the formula that a minus b times a plus b is a squared minus b squared. And therefore, this minus this into this plus this is a squared minus b squared. And finally, this comes out to be 2 times root 11 plus root 9 by square and root both get cancelled, and I get this to be 11 minus 9. And therefore, this comes out to be 2 times root 11 plus root 9, of course, is 3. Though given in the question in unsimplified form, I can substitute this root 9 to be a perfect square to be 3, and 11 minus 9 is 2. Therefore, I see that the denominator is rationalized finally. The denominator which was in roots is no more with any root form. And further, I can simplify this to bring into the more simplified form so that I get my x as root 11 plus 3 is how we get for this. And thus, we finally understand that denominator is finally rationalized. Rationalizing the denominator or the numerator for any given number is possible. Exponents connected with real numbers. Now that we have seen different properties like rationalizing using a plus b into a minus b, which is a square minus b square, and various other properties, now we are going to enter into connecting the real numbers with exponent properties. Laws of exponents, laws of indices is what we are going to talk about. Laws of exponents in real numbers. So let's see how they are collaborated or interconnected with each other. Without the use of laws of exponents, we cannot proceed further by operating the real numbers, is how we understand this session being important and to be learnt in the number system, in the topic of number system. Now we know that the laws of indices are a power m times a power n is a power m plus n, the most famous law of index which you have learnt in the lower classes. Similarly, the next law of index is a power m by a power n, which is a power m minus n, is how we understand this. So based on these two properties, let's see how we can simplify some different examples where real numbers are given in this form. For example, I have a question which says simplify the real numbers which are expressed in the form fifth root of 7 cube root of 7 into root 49. So let's see how we can simplify this strictly using the laws of exponents. Now clearly I see that this can be simplified initially by extracting the roots. So because it's in the fifth root of 7, we understand that nth root of a is a power 1 by n, and hence fifth root of 7 is 7 power 1 by 5, and root 49, which is 7 because root of 7 square, and cube root of 7 is 7 power 1 by 3. So basically when we discuss about laws of exponents, we think of making all the bases equal is the rule we need to identify. So because the given question has different bases, my first target was to make all the bases 7 equal. Now I clearly see that this satisfies the property number 2, that is a power m by a power n is a power m minus n. So replacing a by 7, I get the second law of index, which is a power m minus n, is how we understand this, times 7, never to be forgotten. And here I get this by further simplifying through LCM. I get 7 power 15 3 minus 5 times of 7. So I get this to be 7 power this times 7, which on further simplification gives 7 power negative 2 over 15 times 7, which can be written as 7 power 1. 3 minus 5 is minus 2 over 15 times 7 power 1. Now clearly I see this with index number 1, which is a power m times a power n is a power m plus n. Therefore this times this gives me 7 power minus 2 times 15 plus 1. When the two bases are equal, the powers are added in the product, which on further simplification gives minus 2 plus 15, which on further simplification gives 13 over 15. And therefore my complete simplified process of this problem is 7 power 13 by 15, or this can also be written as 15th root of 7 power 13. So simplifying the given problem is based on the laws of exponents if the problem gives the real numbers expressed in exponent form. Laws of exponents connected with real numbers.